Hi, welcome to this Open Security Summit session in February 2023. And we're going to go back to one of the good old security chestnuts that, for the ones who are doing security for a while, definitely been a lot of on the map. And then, Larkins is going to give us the AppSec guide to cryptography. Off you go.
Thanks for the introduction. Cryptography is sometimes called science of secrets. People often associate it with mathematics. Today, it is integrated into several components that we as engineers work with or develop. Do we need to be a cryptographer to work with cryptography? Not really. As practitioners, all we need to know is the main concepts and tools. And this presentation is aimed at doing just that. This is AppSec Guide to Practical Cryptography. Hey folks, I'm Larkins Carvalho. Before we get started, a huge thanks to Open Security Summit for giving me the opportunity to share my learnings with the community and the members of security industry. Legal disclaimer, all opinions are of my own and do not represent that of my employer. A little bit about me. Currently, I'm product security engineer at Plaid. Plaid is enabling all companies to build fintech solution. We are at the forefront of enabling financial freedom for all. At AWS, previously at AWS, I was application security engineer for securing S3 and new emerging services. Even before that, I started my career at Intel as software engineering intern, contributing to Intel's open source security services and transition to security researcher role. I am an outdoor enthusiast. In my free time, I enjoy hiking, biking, camping with my family. And as you can see in this picture, that's my dog, Tahoe, having fun in desolation wilderness. So the intended audience for this talk is security architects, security engineers, software architects, software engineers, and software developers. Let's do a quick review of our agenda and what we are going to cover today. First, I will go over the overview of cryptography, why we need cryptography, cover core terminologies, some definitions, and what cryptography can provide us. Then we will check out the properties and crypto primitives. Then go over functions of cryptography. What we are going to look here is how the cryptography is used to protect sensitive data and the role of cryptography in public key infrastructure. Then we are going to take a look at two different case studies and like how cryptography could have been used to prevent security issues. And also going to look at how the implementation went wrong for different libraries. Then we are going to take a look at security review and threat modeling, where we are going to discuss the role of threat modeling in security review process and how to do a cryptography security review. Once we are done with the security review topic, we are going to look at guardrails, like how do we build guardrails so our developers won't make unintentional mistakes, and how can we enable them to achieve higher developer efficiency without putting a lot of processes in place. Then we are going to take a look at Google Tink library, how Google have open source some of the very important libraries which developers can use. Then transitioning to verification auditing, we're going to review ASVS, Application Security Verification Standard, and look at what are the different checklists we can look at while doing cryptography security review, and also look at some of the open source tools and static analysis tools which can help us to audit our source code. So by the end of this talk, you will be equipped with a high-level understanding of cryptography and the importance of it in different systems. We are going to take a look at like what are different crypto security reviews, how can we leverage different security tooling, and then what is threat modeling, how can we integrate threat modeling to influence different security controls, and also look at guardrails. So why cryptography? What is the role of cryptography? Let's take a look at two different examples. One, these are two famous examples of like breaches or incidents. So data breaches have been on the rise for years and the trend is not slowing down. Theft of sensitive data is on the rise, and we see them in the news or in different form of media. Two examples here are Facebook storing millions of passwords in plain text. It's not a breach, but still, trust is built in drops and lost in buckets. When we hear some kind of news where our password were not handled the way they are supposed to, we lose our trust in the company, the services and the products they sell or we use. And then we are going to look at like the massive Equifax data breach affecting 143 million users. We are going to take a look at the case study and go in depth in Equifax data breach. Cryptography helps us with data security and privacy. So data classification encompasses organizational policies and procedures. It helps to define what is the different classification of data, and based on that, we can use cryptography to design mitigation to protect it in our systems. And data encryption has different uses based on our security requirements. Compliance. Cryptography helps us to be compliant with different regulations and standards. FIPS is called known as Federal Information Processing Standards. It is defined by NIST, National Institute of Standards. And here they have defined requirements for validating different security components. Like FIPS 140-2 is security requirement for cryptography modules. Like companies like Thales who develop cryptography modules have to be validated. Even the libraries which we use has to be FIPS validated if you want to sell those products to Federal Institute. PCI DSS. PCI DSS is Payment Card Industry Data Security Standard. It helps us protect cardholder information. They have listed guidance on how to store and process cardholder information. And one of the guideline or requirement is encrypting information on public network. HIPAA. HIPAA is a Health Insurance Portability and Accountability Act. It does not actually talks about how to encrypt data, but like there is, I don't know a better means of securing data than encryption. So even if it does not talk about how to encrypt data, we will need to use encryption to protect PHI, which is EPHI data. Then cryptography failures, a new category added to OAuth 2021. Earlier, it was sensitive data exposure, and now it is cryptography failure. As OAuth states, it is from root cause versus symptoms. Earlier, we focused on the symptoms, but not on the root cause. The root cause for sensitive data exposure are cryptography failures. Now, I would like to discuss some core terminologies. So what is cryptography? So cryptography is Greek word. It has two, like cryptos is secret and grapho is writing. So it's a way of writing secrets. Here, Alice wants to send data to Bob, and Alice is like having some kind of a secret data, and only Bob should be able to view this data. And the data is sent over insecure channel. So how do we make sure that the insecure channel, the data which is traversing on public network to be secure? So we use encryption and decryption. Encryption and decryption are two different operations where we hide information from users who does not have a key. So here we have like an encryption key and a decryption key. Encryption key is fit to encrypt operation, and the data becomes now unreadable to human. To make it available in plain text, you need a decryption key. So that is basically cryptography. One of the Kirchhoff principle states a cryptography system should be secure even if everything about system is public except the private key or the secret key. Moving to the definitions, plain text. So we looked at different components here, but what it means, let's take a look at it. Plain text. So plain text is unencrypted data which can be viewed without requiring a key or decrypt operation. So ciphertext. Ciphertext is actually the output of encrypt operation. And to actually view the data, encrypted data, you need a key. Insecure channel is data traversing from point A to point B over public network. Encrypt. Encrypt is an operation, it's a way of converting plain text data into random bytes, and decrypt is the vice versa, where the random bytes are converted to a plain text that are human readable. Encryption and decryption, they are input to encrypt and decrypt operation. They the key to input to encrypt and decrypt operation. So what can cryptography provides us? So cryptography provides us with confidentiality. If I'm sending data to you, only you should be able to view that data. Authenticity. If I am sending data to you, only you should be able to tell the data came from me. What does integrity mean? If I'm sending the data and when you're viewing the data, you should be able to tell this data was not tampered with. Non-repudiation. Non-repudiation is another property where you cannot say like the data was not sent by or signed by me. It should be clearly evident that data is coming from Larkins if I'm sending it to you. Anti-replay is another property of cryptography. It provides us like a way to identify and the reuse of old data. So it comes with the freshness of new data being sent. So let's map it with STRIDE. STRIDE is a threat modeling methodology. STRIDE stands for spoofing, tampering, repudiation, information disclosure, denial of service, elevation of privilege. Cryptography helps us with spoofing, tampering, repudiation, information disclosure. These are some of the cryptography primitives: symmetric encryption, asymmetric encryption, hash functions, MAC message authentication codes, digital signature, randomness, key generation. Now let's take a look each one of them to understand high level what are they. So symmetric encryption. So symmetric encryption is a way of sending data from point A to point B using same shared secret key. So symmetric encryption relies on secret key, which is shared between two parties. Asymmetric cryptography. So in asymmetric cryptography, we make use of two different keys, a key pair of public private. So here, if Alice wants to send data to Bob, Alice will be using Bob's public key to perform encryption and send it over insecure channel to Bob. Bob, to retrieve the data, to recover the data, encrypted data, will use its private key to decrypt and view the plaintext data. A cryptography hash. A cryptography hash is a function which takes arbitrary length message and produces a cryptography hash. So it always produces a fixed length hash, but the message itself can be of any length. Cryptography hash is irreversible, meaning if you have a cryptography hash, you cannot get the message itself. If you want to verify the hash, you need to again pass it to the hash function and compare the hash of the message. They are widely used in digital signatures and message authentication codes, and it does not need a key. Message authentication code. So in message authentication code, we use like the message and a secret key. What it provides is message integrity and message authentication. A hash function just provides message integrity, but not authentication because there is no key involved. So you need a secret key to get the property of message authentication. And it uses symmetric techniques. So construction of MAC can be HMAC, which is hash-based message authentication code, GMAC, Galois counter mode in MAC, and then CBC MAC. digital signatures. So in digital signature, we use asymmetric cryptography. That is, to sign a message, we use private key, and to verify the message, we'll use public key. It provides message integrity, authenticity, and not repudiation. It is widely used in certificates, and some of the algorithms are RSA, DSA, ECDSA. DSA is digital signature algorithm. ECDSA is elliptic curve digital signature algorithm. ESA and DSA have advantage over RSA because they produce very small signatures. Randomness. Cryptography system need a source of random bytes for different applications. And the randomness is used for key generation, nonce, salt. There are different ways of generating randomness. Some of the true random sources are hardware, but they are expensive to generate. For that, we use pseudo-random generators on top of the random sources we get from hardware. Key generation. So key generation is fundamental to any crypto system. Generating key using cryptographically secure number generators, and in symmetric cryptography, we generate one single key for encrypt and decrypt operation, versus in asymmetric, we generate public-private key pair, which are they are key pair, meaning they are associated with each other. Now let's take a look at the bird's eye view of like what we just discussed and what were the different primitives and what cryptography provides. Confidentiality. With encryption, we get confidentiality, but there is little more than what we are discussing here. There are different primitives and algorithms which provides encryption algorithm which provide more than just confidentiality. Hash functions. Hash functions provide data integrity. MAC provides us with data integrity and authentication. Digital signatures provides with digital data integrity, authentication, and non-repudiation. And monotonic counter/nonce provides us with anti-replay properties. One thing I mentioned about encryption, the primitive I was talking about, one of the example is AEAD, authenticated encryption with associated data. It is widely used data encryption technique, and it provides with different security properties, which are suitable for most encryption needs. So moving on to the functions of cryptography. Secure password storage. So with cryptography, we can use cryptography to securely store password. We can use hash functions, but hashing itself is not good enough. There are different attacks like rainbow table and pre-calculated hash. If we just use plain text password, if we just use hash functions to hash plain text passwords. So what we need to do here is use salt and work factor to slow down attackers' efforts. Consider using paper for additional layer of protection. Data encryption. So with encryption, we can store a sensitive data at rest, which even in sensitive data info disclosure, it won't be easily available for attackers. It also helps us to store and process PII and PHI. TLS. So TLS is widely used protocol to encrypt data in transit. It uses symmetric cryptography for bulk data encryption and asymmetric cryptography for key exchange and generating secrets. Let's take a look at two different cipher suites, TLS cipher suites. The first one, 1.2, is TLS. It's a protocol ECDHE, which is ephemeral elliptic curve Diffie-Hellman. That is the key exchange algorithm which is used in TLS. ECDSA used for digital signature, which is again elliptic curve digital signature algorithm. AES is encryption algorithm with 256-bit keys, and GCM is a primitive for symmetric algorithm. And SHA, secure hashing function to generate the hash. In TLS 1.3, it's a little different, where now the cipher suite is shorter. And the reason for that is Now, TLS 1.3 is not supporting RSA because TLS 1.3 provides perfect forward secrecy, and ECDHE and DHA provides perfect forward secrecy properties. Public key infrastructure. So public key infrastructure is a way of generating secrets, certificates, managing them, creating them, and distributing. It provides us with confidentiality, integrity, and authenticity. What is a certificate? It's an electronic document issued by a trusted certificate authority. Now, let's take a look at two different case studies. The first one is Equifax data breach. Before we look at how the attack happened, let's look at the impact. What was the impact? So the Equifax breach resulted in attackers accessing personal information of 143 million individuals, and later it was corrected to 145.5 million individuals. It was also determined that 209,000 credit card numbers were stolen. Data exfiltration happened for 76 days, and attackers actually accessed 51 databases. So what went wrong here? The first one is the attacker got into system with Apache Struts vulnerability. So Apache Struts vulnerability let attackers execute remote code execution vulnerability, and they started looking into systems. When they did reconnaissance, they found out there are plaintext username and password available. And using those plaintext username and password, they did more reconnaissance and got access to multiple different databases. Once they got access to different data stored in plaintext, what they did is encrypted this plaintext data and then started the data exfiltration. Equifax had tools to detect this kind of malicious activities, where even if the data is sent encrypted, they could crack it open, look at the data, look at and analyze what is this data being sent. However, the intended system did not behave properly because it failed to renew the certificate which the systems were using. It was not renewed for 10 months. If they would have had good operational practices of renewing different certificates on time, especially for this critical system, they could have analyzed this issue. If analyzed and avoided this issue. If they could have used cryptography to hash username and password and have tight access control around them, the issue could have been avoided. So as you can see here, attackers got into server through their online dispute. Once they breached online dispute service, they got access to different databases. And once they got access to different databases, they got additional access to 48 more databases. Once they have that access, they started encrypting the data and exfiltrating in small chunks so that it is undetectable. Now let's look at JWT. JWT is JSON Web Token. This was related to some of the libraries. There was no security issue related to what I mean is not cryptography issue, but how you develop libraries and how you do validation for these different libraries. So JSON Web Tokens are standardized format for sending cryptographically signed JSON data between systems. It is stateless. That means you do not need to store JSON Web Tokens on your backend. And there is concept of a claims where you exchange claims with different server to prove your identity. Here, the decoded token we see header, payload, and signature. So JWT token are made up of these three different fields. Header typically talks about what is the algorithm and the type. Payload can be, it has different properties to it, private, public, where you basically encode what is the information you want to, and the signature is computed on top of header and the payload. So in combination, what you see is signature is encoded data of header, payload, and signature. So what went wrong here? So JWT has a concept of algorithm none. That means if you have algorithm with none, the library failed to verify the signature. That means you can basically put whatever claims you want. And remember, the use cases for JWT is authentication, session management, access control mechanism. If we can force this kind of tokens, that means you can do authentication bypass. You can also trick the server in accepting whatever information you want to send. One such is doing privilege escalation. If you're not admin, you can change your claims to admin and send it to the server, and server will happily accept it. Then let's take a look the another vulnerability, which was forgeable public private tokens. So there are two different algorithms which it supports for signature. One is HMAC and RSA. HMAC is symmetric, meaning it uses a single key for encryption and decryption, in this case verification. And RSA is public private, it's asymmetric. So what happened here is, like, if you forge the token with and replace RSA with HMAC, the server will consider it as a public key. So attacker needs to know, a bad actor needs to know what is the public key associated with the public private key pair. Once they understand that, they can force this token, generate a new signature. Now, when the server looks at the algorithm, it treats as this private key and uses its own private key, verifies the signature, everything is good, it will happily accept it. So nothing is wrong with cryptography here. Everything is like a best intention. But if we are building cryptography right, there might be some issues related to the implementation of a library and how we are using cryptography. For that, we need careful review of our libraries and what we use or what we take libraries to build. So now let's take a look at a fun topic, cryptography security review. Before we talk about cryptography security review, let's talk about what is the role of threat modeling in security review. So threat modeling is a process of identifying threats to a system, defining security requirements, and designing mitigation. In threat modeling, we need to ask ourselves questions: what are we building? So we need to model our system, model different data flows, and then we need to think about what can go wrong here. What can we do about it? And did we do a good enough job? When we think about what can go wrong, we are talking about threats. When we talk about what can we do about it, we are talking about mitigations. And once we have mitigation in place, we need to see that are these mitigations implemented as intended? Can we do more? So why do a cryptography security review? So to make sure that the system is designed based on the security requirements and the claims, we need to understand what is the applicability. What is the data at transit, data at rest, data in use? What are the protection needs? What are different privacy laws, regulation needs, regularity requirements? Also need to understand data classification. How do we classify this data? Once we have the understanding of these, we need to carefully do planning during design phase to avoid cost for redesigning and refactoring. Cryptography systems and protocols are difficult to design and secure. So the earlier we do security review to understand our crypto usage, the better. Also, a single cryptography primitive might not fulfill our security requirements. We need to think like what else needs to be done here. Then also threat model sensitive data and like what cryptography mitigations. How can we leverage cryptography to develop mitigations? Once we have the understanding while doing implementation, we need to think about like what are the security requirements in terms of libraries we are going to use. Are these libraries used and maintained by our industry? We need to thoroughly vet the libraries we are using. So what is cryptography security design review? Here we do a thorough review of design and architecture. We look at our security objectives, security requirement, data classification, do secure code review. You might ask, hey, we are doing design review. Why do we need to do secure code review in this case? But like if not all systems start from they start at different point of time as well. Consider a system already in place and now we are making updates to some of the security requirements. That means we already have some source code for review. So if we have that, we should take a look at the secure code. We should take a look at the code and do secure code review as well. And then we need to have a verification and testing plan. So when we are doing cryptography security design review, we need to look at defense in depth controls. We need to look at like, are we developing new cryptography algorithms or protocols, which in my opinion is a huge no-no. Cryptography is very hard to get it right. And if we have anything that we can use existing libraries, protocols is always good. What to look for? So in cryptography security review, we should look for old and big cryptography algorithms which have known vulnerabilities and which use insecure padding. Key management. Key management is industry problem. We need to look at how we are storing our keys, how we are rotating, what is the access control, who have access to these different keys, what permission do they need. Secure handling of key material. Secure handling of key material goes hand in hand with locking of sensitive key material. So key material is the heart of like cryptography. If we are not handling it right, that means we might have like issues even though we have designed a very secure system. We need to take a look at TLS configuration. Take a look at if we are storing passwords and we are storing passwords in plain text, if you're using different kind of salt, work factor, and then also hard-coded secrets. As a warning, if you're using or developing custom libraries or protocol, pay close attention to it. Let's take a look at one threat modeling scenario. The scope of the system is we have a mobile application. User inputs credit card numbers and credit card information, and it goes all the way traversing over internet, and it is stored in database. It's a very simple system. So when we start looking at from security review point of view, the first question we need to ask is, do we actually need to store this information? What is the classification of this data? Can we offload storing credit card information to some third-party services? Because credit card numbers have PCI DSS requirements. If we are storing and processing them, we need to comply with them. So how can we offload some of our responsibilities? If that is not possible, then we need to thoroughly look at our design and come up with threat mitigations and do complete threat modeling process. So now let's take a look at some of the threats. These are just high-level threats. There are so many threats we can come up in this design. But like to keep it simple, let's think about like 3 different threats to this system. One is credit card information sent unencrypted over insecure channel. That is from mobile phone to load balancer. The next threat is attacker getting access to plaintext credit card information. That is from load balancer. That can be anywhere in this system, right? Then SQL injection vulnerability leading to information disclosure. So these are 3 high-level threats we are going to discuss. We are going to talk about the mitigations in the next. So the mitigation here to encrypt traffic or credit card information numbers, it's from mobile to load balance. We need to enable TLS for data in transit. Then for threat 2, Let me go back. Attacker getting access to plaintext credit card information, leading to sensitive information disclosure. We need to encrypt our databases. But we need to also think about like just encrypting data at rest, is it good enough? Like what if there is insider who can crack open the database and take a look at it? At that point, we need to think about like how can we not only do database encryption, but can we leverage field encryption? So if we can do like no, because all data is not like sensitive. So, and we need to think about the performance aspect as well. So if we can get away by just securing credit card information, we should use field level encryption. And how will that help us? In SQL injection vulnerabilities, if an attacker is able to get hold of all the data in the database, because when database gives you data back, it will be in unencrypted form. But there are some sensitive fields in it. So if we can encrypt those sensitive fields even before storing it in database, that will help us to design mitigation against SQL injection vulnerability. Let's take a look at some of the, like what can we do in terms of validation? We can inspect traffic from different components and see if it is encrypted. Like validate data stored in database is incomprehensible. Like fire some queries of database and look, okay, even if we get output from database, are these field encrypted? The intended field or the sensitive field which we want them to be encrypted at all costs. Let's talk about guardrails now. So what are guardrails? So guardrails prevents deviation from expected behavior. So whatever security requirements or recommendations we have, we can define them as policy as a code. So even if we have misconfiguration, before they become reality, we will be able to spot them. We can take a step ahead and even provide primitives or some of the configuration which are secure by nature and disable interfaces which are insecure, which we already know are vulnerable to different vulnerabilities or threats. Tip, even though we have the best guardrails put out there, we should have self-service guidance on these guardrails so our developers can actually use them. One such library I would like to talk about is Google Tink. Google Tink is open source cryptography library written by cryptographers and security researchers at Google. It provides secure and simple API, which take care of common pitfalls and also carefully implements different interfaces which are ready to use. Some of the properties are easy to use. It provides encrypt and, for example, it provides encrypt and sign data operation with just a few lines of code. As we all know, the more line of code we add, the more chances of it being vulnerable or being exploited. So less is more. So if we can get away by writing like just a few lines of code and achieve the same cryptography properties, we should definitely do that. Secure. It adds different protection. In a way, it has concepts of different key handles. And what it does, it provides client-side libraries, which can provide us key management as well. Compatibility. The ciphertext are compatible with existing cryptographic libraries. One thing to note here is like taking a look at the pull request. So when we as like engineers, when our product team or service team reach out to us for different libraries, like can we use this kind of libraries? One thing to look at is what is this library? Who is developing this library? How many pull requests are there? Who like in the like GitHub concept here, how many stars this have? Like how many folks are created? For the maintenance, are there more than one or two maintainers who are looking at this library and keeping it secure? Now, jumping onto the Tink example, I would like to talk about like different how Tink works and what is the piece of code it provides. Like what are different concepts here? The first thing is primitives, another is key types, key sets, and key set handles. So primitives, Tink uses primitives as cryptography building blocks, and it provides different encryption primitives like authenticated encryption with associated data, and it exposes interface, just two interfaces, one encrypt and decrypt. All you need to do is initialize a new handle, provide it a primitive, and now you have a key handle. You don't need to do any kind of like a get the key into clear text, nothing. It will handle it for you. Next, what are the different key types? So the key type implementation is for a specific primitive. Like if you think about AES, then we might want to use AES 128 GCM or 256. And that is again tied to AEAD, which is a key set, the first line in the function main. Then about key sets, the Tink uses key sets for managing keys. So they like facilitates a lot more than just managing keys. You can connect to external KMS. KMS is key management service. You can do different key rotation as well as part of using different key sets. And then key set handles. As we talked about, like how to initialize a key set handle, it uses different, it operates over key sets via key set handles, right? So a key set handle limits the exposure. Like you don't have to deal with it in a plain text key material, and it will do it for you. So there is very less scope of developer doing a mistake. All you need to do is initialize a key set handle, call it a primitive, initialize, and do decrypt and encrypt operation. And most of the things are done transparently. Now let's talk about envelope encryption. So envelope encryption is a practice of encrypting plain text data with the data key and then encrypting the data key under another key. So we have a hierarchy of master key, key encryption key, and data key. And the data is stored in the databases, and the data key, encrypted data key, is stored along with it. So what is a data key in envelope encryption? So data key is actually used to encrypt data. And it differs from master key or key encryption key. Here, key encryption key is encrypted with master key, and the key encryption key will be used to encrypt data key before saving it to the database or to the storage, any form of storage. So what are the benefits of doing this, right? Like if you want to rotate or invalidate different keys, it's very easy to do so. Like if we disable key encryption key here, all the data keys which are there becomes invalidated. You might be thinking, if we are encrypting data and then encrypting data key as well, why not re-encrypt database twice, right? No, because it has different benefits. It has performance benefit. The data key itself is short, and it will result to faster encryption and decryption. How can we do same envelope encryption using Tink? So Tink provides client-side encryption with multiple integrations with cloud service providers. What it does is like it provides primitives and functions to provide KEK URI. Here on the template in the try block, what you see is KEK URI, key encryption key, and it also provides a way of authenticating to it through different credentials. Now that you have a key encryption key with the valid permission, that means the access control is also limited to that particular credentials. You can initialize, you can generate different data key, and it will do it for you. It will do the envelope encryption very transparently. You don't have to write a lot of code to achieve the same functionality. Verification and auditing. So let's take a look at some of the cryptography architecture. So these verification standard ASVS is OAuth's project, and it stands for Application Security Verification Standard. it talks about like different cryptography architecture checklist, as well as it talks about stored cryptography and what are the checklists associated with it. So now let's take a look at some of the checklist items related to cryptography architecture. So I will go over a few. So verify all keys and password are replaceable and as part of a well-defined process to re-encrypt sensitive data. So these actually maps to like think about if you want to, if some of the keys and passwords are leaked, you want to re-encrypt it. So you should have that mechanism. Another thing is some of the compliance requirement also states like you should be rotating different keys and passwords at a set duration. So if you don't have that mechanism, we won't be able to do that. Verify the consumers of cryptography service protect key material and other secrets by using key vault or API-based alternatives. The whole point of this is like we need services who can handle and protect our key material securely. If we don't have some services who can do it for us, it defeats the whole purpose of cryptography. Because if we leak cryptography key material, it's a game over. Attacker can use this key material to decrypt the data and again get access to the sensitive data. Stored cryptography. So stored cryptography is V6 in this document, and it has different components as well. What it says is ensuring the verification satisfies the high level requirements. And some of the requirement it talks about is cryptography module failing in secure manner so that the error are handled correctly. We are using the right random number generators and the access to the key is securely managed. Then there are four different components. One is data classification, two are listed here. Data classification and secret management, but there are two more, algorithms and random values. Let's take a look at secret management 6.4.1. This one is verify the secret management solutions such as key vault is used to securely create, store, control access, and to destroy secrets. So if we have a secret management solution, it is easy to do key management work, key management lifecycle. Verify the key material is not exposed to the application, but instead uses isolated security modules like Vault for cryptography operations. So some of the operations like key generation, they should be done in secure environment. So they should be done in isolated security modules, which are specifically designed for them. And in data classification, let's take a look at 6.1.2. Verify that regulated health data is stored encrypted while at rest, such as medical records, medical device details, and de-anonymize research records. So to be HIPAA compliant, you need to store and process information or medical records securely. So you can use cryptography to basically store them securely encrypted. Also, there are a lot of research going on, and to do the research efficiently, you need to share data. And when you start sharing data, there is always a possibility of leaking someone's personal identity. So how do you de-anonymize research result so that the identity remains concealed and the identity of a user is not leaked? Auditing. So what can auditing help us? It can help us to find implementation flaws. Manual code reviews are exhaustive. It's very difficult to do code review for 10,000 and thousands of lines of code. So how do we get insights into source code to look for cryptography flaws? Note, like even if you can find these flaws or you can get insights, it's very difficult to create that mind map of like how this maps to each and every security requirements we have. But this is a good way to start looking into cryptography by running ad hoc analysis using static code analysis and then getting insights into insecure functions. It can help you answer, are we using MD5? Are we using DES? These are deprecated algorithms which are not recommended to use. Also, like it can help you answer, are we using random functions which are cryptographically secure, or just the random functions which are not? So what is static analysis? So static analysis is software testing methodology. It can help us to find flaws or errors in a source code. We can leverage static analysis to enumerate all possible usage of cryptography implementation based on the rules as we write. So some of my personal favorite tools, SemGrep, Bandit. SemGrep is like you can use SemGrep to analyze different languages, not just for one particular language, whereas Bandit is for Python, the GoSec is for Go, and OAuth has a huge list of like static code analysis tools, which are open source as well as commercial. You can take a look at them and see which one fits your needs. I would like to talk about SemGrep. It's my personal favorite. So it's a lightweight open source engine with thousands of community contributed rules. As they say, it runs code analysis at ludicrous speed. You can write your own custom rules, and they also have open source rules for crypto failures. If you click on this link and take a look at the rules they have, it's huge. Like they have rules, crypto failure rules for different languages, different frameworks, and based on the language and framework you use, you can pick some of them, run a source code, and get insights in how they play. What to get inside, like what are the crypto related implementation in your source code. Also, you can use static analysis tools to run in continuous integration in your CI pipelines. So fixing cryptography failures can be very expensive in production. So how can we get insights as soon as possible when the developers are committing this code, when we are developing certain features? In CI integration, we need to keep this as close as to developers. If it is CI integration, developers spend most of their time there. And before committing this code, before merging this code, we can flag these issues to developers so they even know with the right guidance what can we do, what they can do, and what are the steps they can take. And they hook into any SEM platforms like GitLab or GitHub. With that, we have come to end of this talk, and I would like to open it for Q&A. Oh, that's a great question. What is the difference between salt and paper in storing password? So salt is a unique randomly generated string, and it is added along with the password. So what it does is like when you hash, like consider you're hashing, call it password 123, and even and then we are storing it in the databases, it will generate a hash, right? Now, if attacker get access, or if someone get access to this hash password, what I can do is generate a rainbow table or pre-calculated and look at all the different hashes and then compare it with the database entries. Now you have given, even if you have hashed the password, you have given the password to the entire, whoever is looking at it. So what you can do is use salt, which can be used to in the computation of the hash and stored into the database. The salt will be unique for each and every password you are hashing. That means even if there is a brute force attacks or even if there's a rainbow table, it will not match because the salt is unique here. What it also does is think about a scenario when you want to crack open a huge number of passwords. Now, because the salt is unique, the attacker's effort will be, even if they get hold of it, they can get hold of one single by spending massive computation power. Whereas paper, so what is a paper? Paper is additional layer of defense on this. What paper does is you can use paper which is a secret. A salt is not a secret. I would like to point that out. Salt is not a secret, but a paper has to be secret. And what it will do is again encrypt the hash which we have generated, and it is not to be stored in the databases. So it has totally two different mechanisms to store password securely. Can we run SemGrep in CI to find issues early? Also, static analysis tools are noisy. How can we keep false positive rate low? Yes, SemGrep, you can use SemGrep in CI. Like most of these tools have ability to hook into CI and finds issues early. And to the second question, the second part of question is very tricky, right? Like static analysis tools are very notorious, and we all know they generate a lot of false positives. And how can we deal with it? So when you start with analyzing your source code, you might have some ideas on what are some of the insecure functions you want to look at. So start with them, try to analyze, look at the results you get. Once you have like a good result set, then you can expand your search. But if you go ahead and run all sort of rules, they will generate false positives for you, and it will basically degrade your productivity of like doing the research of what you're doing on auditing your source code. Is Google Tink FIPS validated? Google Tink itself is not FIPS validated, but they provide guidance on how to do that. They have, because it is built, I think for C++, they have some guidelines because it is built on top of boring SSL, and that itself is FIPS validated libraries. Note here is Google Tink, the algorithm it provides are actually FIPS validated, not FIPS validated, but FIPS recommended. So you can basically play around and see like how you can use Google Tink with boring SSL to be FIPS compliant here.
Any further questions from anyone? No, I think that is it. Thank you very much for coming. Thank you, Larkins, for the presentation. It was great. This will be online within the next 24 hours. And Larkin, if you can send me the presentation, we'll get that up on the website as well.
Sounds good. Thank you so much.
Great session. You know, it took me back to, you know, my early days in cybersecurity. A really great and a segment, really cool. Thanks.
Thanks, Denise. Really appreciate you.